This is a quick run through of test number 1. Question number 1 indicates that you're supposed to rank some commodity bundles. Each bundle has a certain amount of x1 and x2 in it. So what we're going to do is plug those numbers into the given utility function, min 3x1, x2. So what we would do in the case of the bundle 210 is write down min 3 times 2, that's what that is, comma 10. And the min function means that we're going to take the smaller of those two. So 3 times 2 is 6, and 10 is 10. So this is really the minimum of 6 and 10. The minimum of 6 and 10 is 6, and that's where the 6 comes from. Okay, so we would repeat that for all 4 bundles, and then we would look at which bundles had the highest utility level associated with them. And what we would find is that the consumer is indifferent between A and B. B is preferred to D, and D is preferred to C. Okay. Next problem asks us to take that utility function and draw the indifference curve associated with U equal 15 and shade the weakly preferred set. So the way that I would approach this first is to identify the corner points for this utility function. So in order to take a min functional form like that one and to identify the collection of all the corner points for all of the indifference curves, you would equate 3x1 to x2. So what we're doing here is finding the corner points by setting x2 equal to 3x1. Now that is not an indifference curve, that's a collection of the corner points of all the indifference curves. That's going to be useful for us later. So now what we're going to do is draw the ray from the origin approximately like that, right? That indicates the corner points. Next, we're going to find specifically the indifference curve where U equals 15. So if we want 15 equal to U, we have 15 equal to min 3x1 x2. Okay? If 3x1 is less than x2, like this case right here, then 15 is equal to the smaller of those two, which is 3x1, or x1 is equal to 5. If, on the other hand, x2 is smaller than 3x1, then x2 is going to be equal to U. And if U is 15, x2 is going to be equal to 15. So we know that our utility associated with 15 is going to have an indifference curve that has 2 parts. One part is x2 equal 15, and one part is x1 equal 5. And the question is, in which part of this big space here is 3x1 less than x2, and in which part is x2 less than 3x1? So we can figure that out really by saying, well, under what circumstances is x2 less than 3x1? Okay, well, this is the line where x2 equals 3x1. So let's take that point, let's say, right here. Okay, so that's a point that's on the ray. If we take a little bit of x2 out of the bundle, so we're down here, we can imagine that x2 is now smaller than 3x1, and so we have the statement x2 less than 3x1 here. If, on the other hand, we started at the point where x2 equaled 3x1 and we added x2 to the bundle, now we would say 3x1 must be smaller, hence 3x1 is less than x2 up here. Once we've identified which side of the ray from the origin we have x2 less than 3x1 and which side we have 3x1 less than x2, we can figure out where these 2 parts of the indifference curve lie. And that's how we ended up with x2 equal 15 here and x1 equal 5 here. So we have this nice right angle indifference curve, corner point on the ray from the origin accordingly. Next problem, what we're going to, oh, sorry, we have to shade the weekly preferred set, and some of you had trouble with that. The weekly preferred set refers to the collection of bundles of goods that are at least as good as the ones on the indifference curve. That means it includes the indifference curve because of the weekly part, and it includes the stuff that's beyond the indifference curves as well. So anything to the northeast of the indifference curve in this case is at least as good as the stuff on the indifference curve, and that's the weekly preferred set. The budget doesn't have anything to do with the weekly preferred set. The budget is simply what you can afford, all right? Now, suppose that Terry has $100 to spend, speaking of the budget, and the price of both goods is $5. We're supposed to graph the budget, so we can do that by taking the two extreme points. There's our income divided by P1 and our income divided by P2, okay? And we know that the budget is going to be the line connecting those points. Now we need to find the slope of the budget. Well, it happens to be -1 or minus P1 over P2, which is -1. And that reflects the opportunity cost of a unit of good 1. So this is a simple case where another unit of x1 requires that you give up another unit of x2, given by the price ratio P1 over P2, 5 over 5. Okay. Next, we need to find the optimal amount of x1 and x2 given the budget. That is the optimal amount or highest utility that we can get from the budget that we have, combination of x1 and x2. So note that there are lots and lots of these indifference curves with corner points along that ray from the origin. And we're trying to climb on to the higher one, and that will happen where the ray from the origin crosses the budget line. Okay? So we can read it right off the diagram in this case. It's 515. If we wanted to solve this analytically, we would note that this is where the ray from the origin crosses the budget line. The ray from the origin crosses the budget line at that optimum point. And that will be true for every min problem, pretty much. So if I solve the two equations, in this case x2 equal to 3x1 and m equals p1 x1 plus p2 x2, simultaneously, through substitution, I should be able to find my x1 star, x2 star accordingly. Okay, now you have some specific numbers in this case, so you have 100 equals 5x1 plus 5x2, and you know that x2 is 3x1, so you can substitute 3x1 into that equation and solve for the appropriate number. We can actually do this one in our heads almost. So 5 times 3x1 is 15x1. 15x1 plus 5x1 is 20x1. That'll give us 20x1. And that equals 100. So x1 equals 5. We could plug x1 equals 5 into here, and we would find out that x2 equals 15. All right, now we're supposed to generalize our solution, and we have some parameters a and b in the utility function, which is going to make this a little more general. We would start in exactly the same way. We would set ax1 equal to bx2 in order to find the ray from the origin that collects or contains all of the corner points from the indifference curves. And that gives us x2 equals a over b x1. We now know that we have a generic budget, looks like that, and that's m equals p1 x1 plus p2 x2. So we're going to solve those two equations simultaneously, the same way we did before through substitution. So I will take my x2 statement here, right here, and I'm going to substitute it into my budget accordingly. If I do that and then solve sort of systematically for x1, I end up with this expression. These are perfect complements, so as P2 goes up, x1 goes down. As P1 goes up, x2 goes down. And we can also see what happens when the taste parameters change as well. Okay. The next version of the same problem requires that we impose a tax. So we have the same indifference curves, the same budget, the same indifference curves or the same utility function, but we have a different budget now. And so our income is going to have to be devoted to our expenses to the seller for x1, expenses to the seller for x2, and our expense to the government for this sales tax, which is based on the value of our spending on good x1. So for every dollar spent on x1, which is given by P1 x1, we have to give T dollars to the government. If we collect terms in x1, we can rewrite this budget accordingly here. And now we can solve that simultaneously with the corner points of the indifference curves via substitution, and we end up with our two expressions here. Okay, so set up the budget by imposing the tax correctly, substitute the ray from the origin corner point relationship into the budget, and solve for the remaining variable, x1 or x2. In this case, we can see that if the tax goes up, x1 goes down, x2 goes down because they're perfect complements, in spite of the fact that the tax is just on x1. In essence, imposing the tax on good 1 raises the price of a unit of good 1, so it shouldn't surprise us that x1 and x2 go down. Next, we have a slightly different version of a utility function. These are what we call perfect substitutes, but we have two different ones. So Henry and Jenny each have their own version of a perfect substitutes utility function, and we can graph a typical indifference curve, which I've done in this particular picture down here. We see that the slopes of the indifference curves are different. Henry has an MRS of minus mu1 over mu2, which is minus 4. And Jenny has an MRS of minus mu1 over mu2, which is minus 1/4, which means that they're willing to sacrifice different amounts of x2 for a unit of x1. So I have x1 here, I didn't label my graph there, and x2 here. Whenever you have differing rates of marginal rate of substitution, you're going to have opportunities to make both parties better off through trade. And that's kind of what this problem is getting at a little bit later in the problem. We know that they don't have diminishing marginal rates of substitution. If that were to happen, the slopes of the indifference curves would have to change as we changed x1 and x2. But these particular slopes remain constant here, and because they remain constant, the rate at which each person is willing to sacrifice x2 for x1 is constant, and therefore we have constant marginal rate of substitution, not diminishing marginal rate of substitution. Down below, what we're supposed to do is figure out whether there is a trade that would make both parties better off. And there is no unique solution to this, so I've picked one such trade. Now we can get some insight into the who's going to give up what in exchange for what from the slopes of these indifference curves. Henry's willing to sacrifice a lot of x2 for an x1. Jenny's willing to sacrifice very little x2 for x1, but that means she's willing to sacrifice a lot of x1 for an x2. So we would imagine that Henry would give up x2, he's willing to sacrifice a lot for an x1. Jenny's willing to give up an x1 for an x2, she's willing to sacrifice a lot of x1 for an x2. So we would imagine that the trade would move in that direction. Another way that you can see this is to look right at the utility function. The 4 that multiplies against x1 in Henry's utility function is the marginal utility of a unit of x1. The marginal utility of a unit of x2 is only 1, so Henry's getting comparatively more utility as he acquires more x1. And so we would expect him to be better off if he gets x1 and gives up x2. Opposite is true here. We would expect that Jenny is better off if she gets more x2 and sacrifices a unit of x1. So I've just taken it to the limit down here and supposed that if we started at the point 10, 10, that in fact Henry gives up all of his x1 for 10 units of x2, and we would imagine Jenny would do the opposite. In that case, we can see how much Henry's utility is affected. His original bundle of 10, 10 gives him 50 as a utility number. Once the trade is complete, he gets 80, so he's better off after the trade. Okay, in this question now we have a continuation of the Henry-Jenny problem, and we're asking for a given budget equation, and this is another case where we have prices that are the same, so we have a slope of -1 in this particular budget equation. We're asking how many units of x1 and x2 Henry will consume. Well, Henry's indifference curves have a slope of -4. Henry's budget line has a slope of -1. So his budget is less steep. That's what this is representing. His indifference curves are more steep. That's what that's representing. And as you visualize this on the chart, you can see that the highest indifference curve that is attainable for Henry is at the corner point where he's consuming all of x1 and 0 x2. Now remember, he thinks of these as perfect substitutes of sorts, and so the question is that given that he's willing to sacrifice 4 units of x2 for an x1, and the market says you only have to sacrifice 1 unit of x2 for an x1, is he going to make that sacrifice? And the answer is yes in every case, and so he ends up with all x1 and no x2. The opposite is true for Jenny. Her indifference curves are flat relative to the budget. So there's our budget with a slope of -1. And the highest indifference curve that Jenny can attain is at the other corner of the budget set. Okay, so what prices for x1 and x2 would cause Henry to consume a positive amount of this good? Well, if in fact, following this red line, the indifference curve lied right on top of Henry's budget, then we would imagine that any point on the budget is going to be just as good as any other, and so he may well end up consuming positive amounts of both. Okay, now we're given the good old Cobb-Douglas here, and this is a plain vanilla Cobb-Douglas to start us out. So our first problem really just asks us to write down what the solution to the Cobb-Douglas problem is. Here's a case where you're rewarded for remembering what the solution looks like. If you didn't, you would have to go ahead and equate the slopes or substitute the budget in the utility function and find the derivative, or use the Lagrange multiplier method or whatever. Okay, but I'm just writing it down accordingly. Now we're going to use the demands and write an expression for the amount of money that this particular consumer spends on good x1 and x2. Okay, now how do we do that? Well, we need to recognize that spending is simply the amount of x1 that we consume times its price in the case of x1, and a similar thing is true for x2. So what we're looking for is an expression involving P1 and x1 multiplied together. So here we have P1 times x1 star. The p's cancel, and we're left with A over AB times M. Similar thing down here. Okay. Now we're supposed to look back at our answer and indicate what the significance of those A's and B's were way up here in the utility function. Well, these are sometimes called share parameters. Share parameters in a Cobb-Douglas. And by the way, this is only in a Cobb-Douglas, not any of the other utility functions. But those A's and B's can be used to figure out what fraction of a consumer's income is going to be devoted to good 1 and good 2. A over A plus B is how much money the consumer, times M is how much money the consumer will spend on good 1. B over A plus B is how much money he or she will spend on good 2.